A ball is thrown horizontally out of an 8-meter high window with a speed of 3 meters per second. At what angle does the ball impact the ground? What is the angle of its velocity vector relative to the ground? Alright, now it sounds like we're dealing with two-dimensional projectile motion. Let's read that again and figure out what information we're given. A ball is thrown horizontally out of an 8-meter high window with a speed of 3 meters per second. At what angle does the ball impact the ground? What is the angle of its velocity vector relative to the ground? So let's draw a picture and figure out what's happening. First, let's draw the ground and the ball starting at a height of 8 meters. The ball is thrown horizontally, so we'll draw the initial velocity vector pointing sideways. The ball is going to move to the right and fall down, so we can draw the ball when it hits the ground and the path of the ball. We're trying to find the angle of the velocity vector when the ball hits the ground. So here's the final velocity vector, and we can label the angle of the vector relative to the ground as theta final. Since the ball is moving horizontally, we're dealing with two-dimensional projectile motion, so we need to set up the x and y axes. We usually place the origin on the ground at the initial horizontal position. Right is the positive x direction, and up is the positive y direction. You can draw the origin with the x and y axes together, or if the picture gets too crowded, you can draw each axis separately. Now we can write out all of the given information, keeping the x and y variables separate. First, we're told the initial velocity is horizontal and has a magnitude of 3 meters per second, which is the speed. If we want, we could write that the angle of the initial velocity is 0 because it's horizontal. Based on the axes we set up, the initial x position would be 0 meters. We don't know the final x position. We know the initial x velocity is 3 meters per second because the initial velocity points in the x direction. We also know the x acceleration is 0 for projectile motion, so the x velocity is constant and the final x velocity is also 3 meters per second. The initial y position would be 8 meters. The final y position at the ground would be 0 meters. The initial y velocity is 0 meters per second because the initial velocity vector does not have a y component. We don't know the final y velocity, but we know the y acceleration is negative g, negative 9.8 meters per second squared. Now that we have everything set up, which equations can we use to solve this? Let's think about how we can find the angle of the final velocity vector. We know that in two-dimensional motion, the velocity vector has x and y components. So if we draw the final velocity vector, the horizontal component is the final x velocity, and the vertical component is the final y velocity. We already know the final x velocity, but we don't know anything else about this vector. So how can we find the angle? Since this is a right triangle, we can use some right triangle trig. If we knew the final y velocity, we could use the inverse tangent function to find the angle. Or if we knew the magnitude of the final velocity, which is the hypotenuse, we could use the inverse cosine function. But we would need to find the y component anyway in order to find the hypotenuse. So let's find the final y velocity and then use the inverse tangent function to find the angle. So which equation can we use to find the final y velocity? This equation has that variable, and we know everything else, so let's use this. We plug in 0 meters per second for the initial y velocity, or the speed, negative 9.8 meters per second squared for the acceleration, 0 meters for the final y position at the ground, and 8 meters for the initial y position. We can simplify that a little and take the square root of both sides, and we get 12.52 meters per second. Now we have a right triangle where the x component is 3 meters per second and the y component is 12.52 meters per second. Technically, the y component is negative, but we only plug positive values into the inverse tangent function because we're just dealing with geometry, and triangles have positive side lengths. So we can plug in 12.52 for the opposite side, 3 for the adjacent side, and we get 76.5 degrees. Also, make sure your calculator is set to degrees instead of radians. So that's what the question is asking for, the angle between the final velocity vector and the ground. This opposite angle is also 76.5 degrees if you want to think about that as the angle the ball impacts the ground. Now let's check that our answer makes sense. It would have to be a value between 0 and 90 degrees because it's this angle inside the right triangle. 0 degrees means the final velocity is horizontal, and 90 degrees means the final velocity is vertical, so this is somewhere in between. If we want, we could use more decimals and plug this value into the equations we used to see if everything checks out.